everybody to our presentation on what's new in Xpress 9.9 Solver. So let me start with a slide that I come back to in almost every release webinar. So this year in a blue color scheme, exciting. It shows that FICO Xpress Optimization is not just a single solver, it's an entire stack of components that build on each other and that fit tightly together. So as a user, you can enter this stack here at very different levels. So some of you may be working with our business solutions, while others interact directly with some of the underlying software components. So you might build your models in Express Workbench, our in-house IDE, deploy them via Express Insight to collaborate with colleagues, and you might maybe prefer to work in Moselle or with Python or call the solvers one of our many APIs. But whichever way you come at it optimization in Express and in FICO, you're all ultimately running the same core underneath the Express solver. And over the next 45 minutes or so, I would like to walk you through some of what's new in that solver and what we've added in the latest release here. Okay, so this is the plan. A lot of the exciting development that we did in this recent release was focused on improving our MIP performance. There have been interesting developments elsewhere as well, so especially around our primary hybrid gradient. There's some interesting news. And there's been some changes to our global solver and to SLP that I will also try to cover, but as you can see from this list of performance-related items, a lot of what I'll be talking about today is going to be MIP performance. And I admit that I might be a bit biased here, given that MIP development is where I come from. But I would like to share my excitement for all these news with you here. Okay, I will not really cover the higher level APIs that we have around the solver. Those have been covered in the release webinar by Susanne. I'll be mentioning a bit about news in our C API, where there's been a few changes that, of course, then also carry over to other higher languages. And I would just want to mention that around Python, we've added support for Python 3.14, and we're dropping support for 3.9. And we've also added support for Pandas 3. And I would like to highlight here, because we won't mention this later in the talk, that there have been some changes in the supported platforms with Xpress 9.9. Most specifically, we are finally dropping support for macOS on Intel CPUs. It's been some time now since Apple switched from Intel CPUs to their own ARM-based Apple Silicon platform. So in Xpress 9, there will not be a version for macOS on Intel. We also slightly increased our minimum requirements for our Linux ARM distribution, which is now in line with the Intel Linux distribution. Specifically, we are requiring a minimum of Red Hat 8 or equivalent. And finally, for Windows, we are dropping Windows 10 and Windows Server 2016 support. Mostly because Microsoft is dropping support for those as well. So we go with the next tile. Okay, so let me get into what's new on the MIP performance side. So one of the exciting things that we've been talking about lots about in the past year, and also on different scientific conferences, has been our highly parallel prelude heuristics. So this is a special composition portfolio, however you might call it, of many different search heuristics that is run and expressed before the initial LP relaxation is solved. It essentially consists, as this diagram here shows, of two phases. One where we try to improve the feasibility of some starting solution that goes into it, and one when we are trying to improve the objective. And then we alternate between these two until we have a feasible solution. And at that point, we just keep trying to improve the objective further and further. And in between, we try to join some of the results of individual subnets that are solved in each of these phases here. Okay, so that's a highly parallel framework. As I just said, each phase will try to set up multiple subproblems by fixing some randomized set of variables and then solve the resulting smaller MIPS. And yeah, each of those will then hopefully produce an improved solution. And as mentioned, there are some initial solutions going into it. So these initial solutions, if there's not already one present in the problem, they come from some quick sequential heuristics that we run. And when we are in the main cycle and the parallel submits keep producing new solution candidates, we then try to join them together. So when we have that, we again apply several different kind of local improvement heuristics, something like a feasibility jump, shift and repair, shift and propagate, which form an ensemble of local improvement methods. So it really goes back between large parallel neighborhood search heuristics in one of the two main phases and these quick local searches in between, plus a method to joining these solutions together. So all of this is existing technology we've had since 9.8, and we have already talked about at conferences and in the 9.8 release webinar half a year ago. So if you are a recurring visitor here and thought, hey, hang on, wait, Timo, that sounds oddly familiar. That's why you've seen this before. But the potential challenge with this existing setup here is that it's run before the initial LP relaxation solve. So it could potentially run for a long time. So you as a user have to decide how much time you want to give it. And anytime you give it to give to these pre-boot heuristics is then being kind of taken away from starting the actual initial LP solve and going through cutting planes and bunch abound subsequently. So there's a trade-off involved here. So what's new now in Express 9.9 is that this highly parallel heuristic frameworks can now also be run concurrently with the initial LP solve. So while we are solving the LP, which already runs concurrently using, well, mostly dual simplex and barriers, sometimes primal simplex joins the mix, there will now also be additional threads dedicated to these parallel heuristics. So as they find solutions, those solutions will be returned deterministically to the user, as we see in this example here. So in between your LP log, you suddenly might get solution found, solution found. So this here is from a 16 thread run, I think. So there will be 4 threads dedicated to heuristics. There's 1 thread for dual simplex, and the remaining 11 threads go to barrier. Okay. So that means really that now, while we are still solving the initial LP to get the dual bound, primal solutions already keep dropping in nicely. So the current strategy, so the current default strategy is that this is off by default settings, but if you enable our special heuristic mode by setting the heuristic emphasis control to 1, then we will dedicate about a quarter of the threads to these new parallel heuristics. So this is what you see here. This is a run that has been conducted with heuristic emphasis equal to 1. And yeah, these threads otherwise would have been allocated to a barrier solve and concurrent. And if you want to fine-tune, there's a new control to explicitly set the number of threads you want to use for these parallel heuristics. And of course, everything running concurrently here is deterministic. So repeated runs will always produce the same results. Okay, so these parallel heuristics start up once the initial LP relaxation starts, and when the LP relaxation has been solved, we terminate the heuristics. So it should not really add much overhead beyond any potential synchronization, of course, and beyond taking away some threads from barrier. So in heuristic mode, when this is enabled, it adds about 2 to 3% improvement on our primal dual integrals, measure for the speed of conversions of the bounds on the solution. This is our standard measure for measuring heuristic performance. And if we just look at the primer side, meaning how fast we improve solutions, since we don't have an LP solution or best bound yet, we see about a 5 to 6% improvement in finding the initial solutions faster. So that's pretty nice for everyone who looks at solving those hard MIPS where optimality seems out of reach. But finding a good solution fast is the challenge that you are up to. Okay, so what's the difference between what we had in 9.8, where we ran it before the initial AP solve, and now where you can also run it concurrently? So yes, you can still do both. In 9.9, well, you can do the one after the initial AP solve, concurrently to the initial AP solve, sorry. And you can also do it before the initial AP solve. So those are two separate stages of the solve. And the key difference is that if you want to run it before the AP solve, Xpress needs to know for how long it runs, for how long you want to run those heuristics. So that's why you have these limits as a pre-root work limit. So a pre-root deterministic work limit or a pre-root effort control that scales what we consider a reasonable amount of work for such heuristic. Whereas for the LP concurrent heuristic, the time is determined entirely by how long it takes to solve the initial LP relaxation. When that's done, we terminate the heuristic. So there's some difference in logic here. We also try to detect whether we are making progress for the pre-root mode. So if we've gone through 5 phases without any improvement, we would also terminate. So you're not guaranteed to hit those limits. The heuristic can bail out prematurely. Okay, then on the other hand, while running concurrently with the LP solve, we just run for however long we have, since it will be terminated automatically anyway. So yet another difference. As for thread allocation, before the LP is solved, there's nothing else really running. So the pre-root heuristics can just use all the available threads, or you can override this with the pre-root threads control. And when running concurrently with the LP solve, we don't want to take too many threads away from the LP. So as we just discussed, we would allocate 25% of the available threads. And there's a dedicated LP background threads control to change that. Okay, and so while the underlying mechanics and the heuristics are the same, as you can see, there are quite a few differences in detail, and the one or the other might fit your personal use cases better. And while you can always activate either of these via the dedicated controls, I think I should point out that they get enabled automatically via our heuristic emphasis control. So in particular, your emphasis equals to 1, as just mentioned. This is also something that a lot of our clients are using for problems where the focus is on good primary solutions and a small gap rather than an optimality proof. Here, our new LP concurrent heuristics will from now on run in the background. For pre-root heuristics, those would only be enabled with heuristic emphasis equals to 2, or with one of those settings here. Yeah, I think it's fair to say really that if even solving an LP is out of reach for your MIP application, then by all means you should go for the pre-root heuristic variant. And if you want to hedge your bets or give your MIP cut loop heuristics a little head start, then LP concurrent might be the way to go for you. So, and if all the emphasis is on the optimality proof, then maybe you don't want either of them. Okay, so yes, this all these concurrent heuristics were about using available threads. Some were doing the solve, and this is also something that we've worked on in other aspects. So this framework that we just discussed is based on what we've introduced as background tasks, so auxiliary helper threads that do additional work typically running heuristics to bring in new solutions, while the main thread is doing the heavy work of solving IPs or generating cutting planes, doing the main lib search. And we are essentially trying to find something useful to do for all these spare cores in the early, mostly sequential phase of a MIP solve, which is the root node execution. So pre-root heuristics, concurrent heuristics, they all use the same background thread framework, and we also run this in parallel to our cutting plane generation loop. And there are various user controls where you can influence how many background threads we run and which algorithms, heuristics in particular, we want to run there. And in this Xpress 9.9 release cycle, we've been improving on what we run in the background, not only during IP, but also during the cutting plane loop. So we've been gradually adding to the mixture over several releases. Here in the beginning, it was just pure heuristics. Now we have things like a fast branch and bound algorithm, which can actually return and improve dual bound to the main thread. And yeah, we might also declare a problem solved by these very quick branch and bound in the background. So there's new exciting algorithms coming in. And we are also running some different kinds of local searches, like a feasibility jump, fix and propagate. They would run at this state. And what we've done in 9.9 is that we've improved the mix of background heuristics, and that translated to some nice one improvement in time to optimality, 2% on hard instances, and about the same improvement in the primary to integral in our heuristic emphasis mode. So some nice improvements from new and better background heuristics. Let me now shift topics, even so we stay with the heuristic emphasis, but we go away from the parallelization and background spreads. So one of the features that works very well for solving problems to optimality is strong branching. So here you take integer variables that are at a fractional value, and you want to decide how good of a branching candidate there are. One of the best things that you can do there is to perform what's called strong branching. So you try rounding the variable up or rounding it down, solve the resulting AP relaxation, and see how the objectives change. And you use this objective change of both of these directions, combine them for an estimate of how good branching on this variable would be. So, of course, this requires solving two APs. So while it's effective, you get a really good estimation of the impact. It can be very, very expensive since you're solving APs for all your branching candidates if you want to apply the same selection criteria to all of them. So there are a lot of techniques that limit how much strong branching you actually do. And one is the concept of history costs, also known as pseudo costs. If you've already done strong branching on a variable somewhere else in the tree, you try not to do it again. You just instead prioritize variables that you haven't seen before. And for the other, you use historic information. Well, now in the heuristic emphasis mode, which is aiming at finding good solutions as fast as possible. So what you really want here is that you explore the tree quickly, so you can get down to some of the good improved solutions. So strong branching still is kind of important for guiding the search and good for selecting branching variables, but it can make those first dives, as we call them in the branch and bound tree, very expensive. So reasonable trade-off there is to make these strong branching evaluations as cheap as possible. So that would be good if you could achieve that. So, and one way that you can do so is by setting the iteration limit low, very low, as low as possible, namely to one iteration. So you're effectively performing a single dual pivot there just to evaluate the branching candidate. And the benefit of single dual pivots is that you can compute them without executing any pivots at all and without any refactorization. So they are very, very fast to calculate. So also means that you can apply them to more candidates at the same time. So this is something that we are doing now when heuristic emphasis is set to 1, and it has produced another nice 2% of performance improvement on our primary integral. Not necessarily time to optimality, of course, but it's an improvement in finding good solutions earlier. And that will show up as an improvement in the primary integral. And yeah, I mean, from the last 2 slides, you already get the idea of MIP development these days. 2% here, 1% there, 2% from another project. And step by step, you build up a really nice overall improvement of the solver. Speaking by another nice yet small improvement, that's a bit away from heuristics, we shift over to cutting planes. So we have implemented the class of cuts called path mixing cuts. They have been in the literature for quite some time already, actually. So these are cuts for some special kind of flow structures, specifically mixed integer flow paths. Imagine a problem like a lot sizing problem. So in each time period, you have a certain demand and a certain inventory, and you have to decide whether to produce anything or not, live on your inventory. And you have a binary decision at each time period, and you carry inventory from period to period. So this is the kind of problem illustrated here on the slide. It's called a lot sizing problem, but it also comes in more complex settings like network design or supply chain problems. They have very similar types of substructures in them. So we've implemented a special type of cutting planes for the structure. They are called path mixing cuts. They are closely related to mixed integer rounding cuts, but for this particular structure, they can produce stronger cuts. So heuristically try to find these paths in the problem and then generate the cutting planes using our existing cutting plane machinery. And path mixing cuts are on by default, so you don't need to worry about enabling them. They will just be there. But you can turn them off if you wish to by clearing a bit of our cut select control. So overall, they don't really have huge impact across all problems, but they do help on problems with exactly this kind of flow structure, which are not that many. So those are some things that you would find in manufacturing, and we observed really the nicest speed up here also in manufacturing and retail type problems. And well, obviously, if you really have a lot sizing problem in its purest form, this should also work very well. Okay, staying with cuts. Another class of cutting planes we've had in Express for a very long time are zero half cuts. So the concept here is rather simple. You take a set of constraints with integer variables and integer coefficients, like in my example, all coefficients are 1, as easy as it gets, and all the variables are integer, maybe even binary. And then you add all of them together with a factor of 1/2. So that's what happens here. And if the sum of the right-hand side is odd, then you end up with fractional variable coefficients like here, and then you can round that down. And also, after rounding all the left-hand side coefficients, you hopefully get a cutting plane that cuts off the current LP solution. So both these and these here are valid linear inequalities for your original problem, and this is the so-called Schwatter-Gomery cut, or a specific form, the 0.1/2 cut. Because 0.1/2, because all the coefficients are 1/2 or 0 for those both that you don't consider at all. Yes, of course, there are a lot of heuristics involved in figuring out which particular constraints to combine to generate such a violated 0.1/2 cut. And the challenge here really is the constraint selection. So yeah, which constraints do you want to add to together. And the only requirement really is the inequality of the variables and integer coefficients. And the right-hand side should add up to an odd number so that you can get this effect here. Also, these cuts are numerically very nice because you end up with all integer coefficients on the left-hand side. And of course, the right-hand side. You round both. You round everything that's involved after you aggregate it. Okay, so far, so existing. We've had that for a long time. And since Express 8.5, we also had some specialized zero half-cut algorithm for that addresses binary quadratic problems. So when products of binary variables x1 times xj are linearized via McCormick inequalities in pre-solve, the resulting relaxation here is often weak. So that makes cutting planes important, especially for dense quadratic matrices. And yeah, the special algorithm that we had here identifies which McCormick constraints are binding, prunes some singleton constraints, reduces the separation problem to finding an odd weight cycle, like this here in the graph where vertices are fractional binary variables and edges reflect whether a shared constraint has an odd or an even right-hand side. And this was originally scoped to the binary quadratic case, but when we investigated whether the RLT cuts that we recently introduced helped make them redundant, we found actually the opposite. Those graph-based zero half cuts still remain beneficial, and they extend to general MIPS as well. So in Express 9.9, we now enable them for general MIPS, not only for those where we think those are linearizations of quadratic constraints. And that again needed a nice performance improvement, 1% time to optimality, 2% on hard instances. Okay, let's look at pre-solve, turn over to pre-solve. So one common construct in optimization problems are soft constraints. So you'd like a constraint to be satisfied, but instead of imposing it really as a hard constraint, so instead of writing some x equals r, you allow for some violations, but you penalize those. So those additional slack variables here would be penalized in the objective function. So in this case here, there's a positive and a negative slack added. And in the picture that you see here, so the dark blue line is the constraint that you would actually want to hold, and the red arrow indicates the violation in one direction, and the green arrow the violation in the other direction. Ideally, you would want both of them to be 0. So the difficulty for a MIP solver is that it's quite hard to do any bound propagation on such a constraint because either penalty variable can absorb any slack here. And what we've done in pre-solve is to introduce a special reduction that checks whether the left-hand side sum is provably always greater than or equal to the right-hand side or always less or equal to it, in which case one of the penalty variables can never pick up any slack and then be consequently fixed to 0. So, of course, this assumes that, fixing them to 0 assumes that neither of them appears in any other constraint. Okay, so this gives only about a 1% improvement on hard instances, but of those problems that actually have the structure, it gives more like a 10% improvement. So it rarely applies, but if it does, it's quite impactful. Okay, and also in pre-solve on the symmetry side, we've had LP folding for quite a long time. So LP folding is a procedure which reduces a problem based on symmetries in continuous variables. And looking at the example on the right here with the blue and red variables, you might convince yourself that if you swap the blue variables with the red ones, so x1 for x2, y1 for y2, y3 for y4, you can get an equivalent solution that satisfies all the constraints. So you could potentially eliminate this symmetry by setting x1 equals to x2, y1 equal to y2, y3 equal to y4. And for continuous variables, that's all fine. You are just distributing values between those two variables. So that's what LP folding does. But for integer variables, this can be a problem, at least in general, because the average, when you are distributing things between two integers, might not be integer. However, in special cases, so like where x1, x2 are binary and do not appear together in the same constraint, as it is the case here in my example, it is still safe to set them equal to each other and carry out this reduction. So this is something that we now do in pre-solve. So yeah, here in the example, the x's are integer and they are not linked to each other in any constraint. So x1 and x2 do not appear in the same constraint, and the y's are linked by the two middle constraints here. But that's okay because they are continuous. So we can conduct this reduction here, even though integer variables are involved. Again, a 1% improvement in time to optimality doesn't apply that often, but where it applies, it gives rather something like 20% improvement. So again, can be quite impactful for those models that have this structure. Okay, that was a fairly rushed tour through our MIP improvements of the past release cycle. There are other minor things that I don't really have time to cover here, but there have been more MIP improvements. But I would like to also turn to our other solvers. So let's look what we've done on the LP side. So about 2 years ago, we introduced the prime module hybrid gradient method, or PDHG in short, to Express. And that's a factorization-free first-order method for solving linear problems. Was originally described in a very well-received by some great researchers. It scales very well to very large problem sizes because it doesn't need to build a factorization. So it uses really not more memory than it takes to represent the coefficient matrix itself, plus a few arrays such as the right-hand side, the objective, and a few auxiliary arrays. So all you need to do in each iteration of PDHG is set suitable for the kind of massive parallelism that you find in GPUs. So in Express 9.8, we introduced a GPU version of PDHG, and it showed some very nice speedups over the CPU version, something like a factor of 50 on some instances, and typically a factor of 5 on most of the huge instances. So there's really some improvements to be gained if you have if you are solving a large AP and you're doing this on GPU instead of CPU. And yeah, the way to enable PDHG is to select the barrier algorithm and set the barrier algorithm control bar arc equals to 4. And what's new in 9.9 is that we introduced a variant based on the PDLP plus work, which uses some different upstates, different scaling methods. It's a different flavor of PDHG, if you wish. It's generally more robust, but it's not universally superior to the other one. It solves some like a different flavor of problem, and in fact it can be slower in some instances. So but it solves some problems that the classic PDHG doesn't handle that well. So it's likely best if you try both and see which works better for your problem. So as a side note, also if you have a machine with with multiple GPUs, there's now a new GPU CUDA device control to select which GPU you want to use. Yeah, that's also a new feature here. And here we've put together some performance numbers for these PDHG methods. They are based on an internal benchmark set. That's a mixture of some public benchmarks, those like you would typically see for PDHG comparisons, along with instances from clients and a selection of other internal instances. So in total, we have 216 instances, out of which 172 can be solved by at least one of the two PDHG variants, so that we see here. So we ran this with a 1 hour time limit, which is fine for the GPU versions. Could say it's a bit tight for CPU. And yeah, some problems that take a couple of hours of CPU, the GPU would here just solve well in under an hour. So in a sense, it's a bit biased in favor of the CPU since we count the timeouts at exactly 1 hour. And the table on the left shows that the GPU versions solve more instances. That's what you see here. Both versions solve more than the CPU versions. And the table on the right, where we excluded problems that solve in under 10 seconds on the CPU, since you wouldn't typically bother with the GPU for those, shows the GPU is quite a large factor faster here if you compare those runtimes. So we tested on a few different GPUs available in Amazon Web Services, the T4, which has been around for a couple of years, the L40S, which came out about 1 to 2 years ago, and the very recently introduced RTX Pro 6000, which is based on a new Blackwell architecture with some 96 gigabytes of GPU memory, I think. And yeah, this is kind of a best currently available mid-tier data center GPU if you don't want to jump on a H100 or B200 or something like this. So what the numbers show is that Express 9.8, the GPU was about 5 times faster than the CPU on average, and in 9.9 we are now seeing an 8 times speed up. So there have been good improvements to the GPU implementation. Specifically, it's not just the underlying algorithm that's improved, but also our way of porting it to GPU, if that makes sense. Okay, still on LP news, when crossover is disabled, as it is typical for PDHG, by the way, and sometimes for Barrier, the result that you get of your LP solver is an interior point solution without a basis attached to it. So this means that there may be constraint violations, no strict complementarity, and dual can be non-zero even if for constraints that isn't exactly tight. And this has in the past caused problems in post-solve, which traditionally assumes cleaned complementarity to determine which variables go basic or non-basics and how to assign the duals. So we've now improved how dual variables are allocated during post-solves when reversing pre-solve reductions specifically to minimize complementarity violations. And the result is a much better dual solution quality, not because Barrier was finding wrong solutions, but because now assigning dual values more carefully during post-solve. So one very extreme example where this helped a lot can be seen on the slide here. Okay, linear conveys nicely into nonlinear. So moving on to the nonlinear side, global solver with Express nonlinear. So there are mostly small improvements. Nitro has been updated to the latest version 15.1. We have done some work around initial values. We no longer use the default initial values control. In particular, we've improved some things for multi-starts here. So the multi-start feature has a function called Xpress multi-start add preset, which creates multi-start jobs with randomized initial values to improve the chance of finding different solutions. And one issue was that it would only assign an initial value to a variable if it had been explicitly declared as a nonlinear variable, regardless of whether it appeared in the formula or not. Also, like if you read in from an n L file that would explicitly mark variables appearing in formula as nonlinear, but that wasn't happening consistently when reading from an LP file. So we've now made all of this much more consistent. Multi-start presets will create initial values for any variables that appear in a nonlinear formula, regardless of whether you explicitly declared that variable nonlinear or not. So this means you get the same behavior when you read from an MPS file, an LP file, an NL file, and you no longer have to do these explicit declarations. And on the global solver, one smaller change on problems where the relaxation is unbounded. We, for technical reasons, need to impose a bounding box around the problem. So previously, we applied this to all variables, but we now apply it only to the nonlinear variables, those appearing in formulas, and use a two-stage approach here. We first try to bound the original variables, and only if that doesn't work, we bound the auxiliary variables. So there have also been improvements on how we scale the auto approximation cuts and convexification cuts that we generate. So auto approximation cuts are generated for convex MIQCPs and second order count problems, and convexification cuts are generated in the global solver. And the improved scaling ensures that cuts are properly detected as violated when we expect them to cut off the LP solution. And yeah, what else? As a side note, we also enabled strong branching for convex MIQCPs now by default. Okay, let's look at what's new on the API feature and usability side. There are two somewhat bigger updates there. Firstly, we introduced a new function, Express Trigger Restart, that can trigger a MIP restart while solving the problem. Up until 9.8, this was a purely automatic feature. If Express detected the right conditions, it would stop the current branch amount search, go back to the root, consolidate all the information gathered so far, apply a new pre-solve, and essentially start everything over. But then starting with all the accumulated information from the first one before the restart. And the new function now allows user to trigger this themselves from anywhere during the tree search. So, for example, via a callback. The only restriction here is that it only applies to linear MIPs, not to nonlinear problems, global solves, quadratic problems, and so on. So, yeah, typical use cases here would be that a user knows by some business logic that is not visible to the solver when a good point to restart is. So that might be based on past experience, that you have observed that whenever you hit a certain gap, or say whenever you find a first feasible solution somewhere in the tree, you observe that now pre-solving works much better, some cuts work better, so we'd likely want to rerun some of the solver's root node heuristics. And yeah, now there's a way to enforce this. Or you generally want to try solving the problem with two different settings because you know that such a portfolio approach works best for your types of problems, but you do not want the solver to start from scratch, but it should keep as much information as possible for the second one of your portfolio solve, not only solutions, but global variable, fixing cuts, branching statistics. So calling Express Trigger Restart is a way to achieve this. And then secondly, we've introduced a new MIP stop stage control. So when solving a MIP, the solve goes through several stages before the initial LP solve, after running the pre-root heuristics, after the initial LP solve, after all the root cutting and heuristics, and so on. And each of these is now a potential stopping point where the optimizer can return control to the user, and you can resume from any of those stages. And new control lets you specify which stage to stop at, inspect the solving process, maybe decide to trigger a restart, and yeah, then either terminate the solve or continue. So when you call Express Optimize or Express Optimize again, it didn't terminate the solve, it will start from the next stage. It will just continue the solve. Okay, there's also a new stop status attribute you can check to see whether the solver stopped at one of these stages. or at which of these stages it stopped. And one of the motivations for introducing this is that we have deprecated the L flag for Xpress Optimized and Xpress MIP Optimized. So this flag told the solve to stop after the initial LP. And the problem was that different optimization functions had somewhat different interpretations of that flag, and everything was a bit messy there. So the new control makes it unambiguous when you want to stop, and it also lets you stop at different stages, not just after the initial LP. So a proper upgrade in functionality. So yeah, accordingly, we've now marked the L flag as obsolete across all optimization functions, which are listed at the bottom of that slide. And some of these, like minim, maxim, have been obsolete themselves for quite some time and might be removed in the future. Okay, a few other minor changes worth mentioning. So you can now repeat all of pre-solve multiple times if you think it might have missed some reductions by setting the pre-solve passes control. Setting it to 5, for example, will run all of pre-solve 5 times. And some reductions that are considered expensive and are only applied once, but with this setting, you can try them again on subsequent passes. So there's also a new control to limit the disk space used by the MIP search tree if the tree grows too big to stay in memory and gets written to disk. You can now make sure it doesn't accidentally flood your entire disk by setting this control. Okay, and while not covering all the higher language APIs, let's at least quickly look into Python and some third-party APIs. So on the Python side, we've continued our work on API consistency. At this point, it's really just some final cleanups and smoothing. This included this time introducing some global module-level functions such as get version, new branching object functions, and the ability to omit the first and last argument of express object names, which now defaults to some sensible predefined values. And something that several users have asked for is the ability to give meaningful names to constraints. So this matters in a number of situations, for example, when listing an IIS, when displaying problem information, or simply when generating a matrix where you want constraints to be identifiable rather than just numbered. So we've added a few flexible ways to do this. The simplest case is just adding a name directly when you define a single constraint. Obviously, if you have a list of constraints, you can provide a matching list of names, or you can provide a single name as a prefix, and it will automatically be completed with the index of each constraint. The same idea works for dictionaries as well. You provide the name prefix, and it gets completed with the dictionary key, giving you some meaningful identifier for each entry. And as already mentioned earlier, we're adding support for we added support for 8.14. We are dropping Python 3.9, which is now end of life, and we added support for Pandas 3. Okay. And beyond our own interfaces, there are quite a few external interfaces to Express maintained by third parties and the open source community. So our modeling and API team has been actively contributing to several of these recently. And I would like to take a moment to highlight what's been done here. So for Google OR tools, Jump and PyOpt, those interfaces have been almost completely rewritten, modernized, and feature completed, or extended such that they integrate Express much better now and offer more functionality. Then there's Minisync, where we completed a full migration of the Express solver wrapper from the old BCL layer to the native Express C API. And along the way, we added support for indicator constraints, warm starting, message callbacks, bilinear and convex quadratic constraints. Updated all the solver controls to the 9.8 with some graceful handling of deprecated controls. And for CPX CVXPy, we modernized the Express interface to compatibility with latest versions, keeping backward compatible fallbacks for users on earlier versions. Same for LinoPy, which is the modeling layer underlying PyPSA. We updated the Express integration for 9.8, while again preserving compatibility with older versions, migrating deprecated method calls. And speaking of PyPSA or PIPSA, as some call it, we also contributed to PyPSA Euro, which is the leading open source European energy system modeling collection. So we added Express server configuration support there with some performance-tuned parameter list, and it supports both CPU and GPU execution modes. And for Ample, I mean, we are not maintaining that interface directly. It's open source, and the Ample team has contributed documentation updates. And the way we provide documentation is through a reference list on the FICO GitHub. That's also linked here. So that's a place to look if you want to stay current with what's supported. In particular, if some of you are maintaining some of these third-party updates, this might be a very, very valuable resources to you. And there's also a nice blog series on third-party APIs on our community page. Okay, now the highlight of each release presentation, performance numbers. This is the year-on-year improvement table that we traditionally show in these webinars. So a year ago, the current Express release was 9.6, and what you see here is how our new 9.9 compares against that baseline of Express 9.6. The numbers come from our internal benchmark sets, which mix public and client models. The client models are carefully sampled to make sure no particular application area dominates the results here. And we report shifted geometric means of runtimes, except in the PDI heuristic emphasis row, which is where we use the prime and dual integral instead. That captures how quickly prime and dual bounce, and therefore the gap converge to each other. And as always, we pay special attention to the harder instances, the ones that take more than 100 seconds to solve. And yeah, honestly, we're very happy with what we are seeing here. LP, MINLP, MIP, our core solvers all come with some very nice year-on-year improvements. So the core MIP benchmark reaches 17% on hard instances, which is strong. For our newer algorithms, where there still is a lot of room to grow, the gains are even more dramatic. PDHG is a factor 2.5 faster than it was a year ago. And the global MINLP solver is 82% faster on the hard instances. Both are also solving significantly more problems to prove optimality. So yeah, really PDHG and global optimization are practically usable capabilities now. And it's great to see that users already pick them up and put them to work. And the speed up of the LP in the first row, so this is a bit artificial, mostly comes from us changing the default out-of-the-box algorithm to be concurrent now instead of dual simplex. So that also means if you are an LP user, you like your default dual simplex as it was so far, you might want to change the LP flex control now to continue using dual simplex exclusively. And the final note, there is no number for PDHG on GPU here because we introduced it less than a year ago, so no year-on-year improvements. Okay, finally, for the last few minutes, some announcement. Our Express Best Paper Award goes into its 5th year of existence. We'll have a 2027 edition. So here you can hand in scientific papers that used FICO Xpress in their work and win yourself a nice little monetary prize and, of course, visibility for your work. The 2027 edition is going to be officially announced in a couple of days, but you can follow the link already if you want to learn more. The deadline is still some time to go, but remember your paper needs to be published by then. And it's a real pleasure for me to announce for the first time publicly the winners of the 2026 edition. Michael Kaut for his great work on handling of long-term storage in multi Horizon stochastic programs using FICO Xpress published in Computational Management Science. And also in this year, there was a runner-up paper by Juan Villegas and co-authors on supply chain redesign and pricing for biomass ash valorization as supplementary cementitious materials. Congratulations, both teams, excellent work. And yeah, if you would like to learn more about Express, make sure to explore the resources listed on the slides. If you haven't already, our community portal brings together blogs, training material, all kinds of helpful content. You will also find the blogs of previous year winners and runner-ups of the Best Paper Awards, and soon those of this year's. Our user forum is the place to go with your questions. We're always happy to help there. And for those in academia, don't forget our academic partnership program, which provides full Express licenses free of charge for research, perhaps even for some work that ends up winning a Best Paper Award. So we reached the finish line and almost the top of the hour. Thank you for listening in, and I'm happy to answer any questions.